Hello friends, I welcome you on BYJU'S Exam Prep, India's most comprehensive preparation platform for all the engineers. All the candidates who are joining me live, just quickly confirm your presence in the comment section and tell me whether my audio, visual quality, everything is clear so that we can start with the session. Till you are going to report me this, let me just brief you what is the ideal duration and what is the agenda for today's session. Friends, the ideal duration of this session is going to be approximately 45 minutes, and the agenda or the outcome of the session is that today we are going to talk about one of the most important concept for your subject power system as far as GATE 2023 is concerned, that is reactive power compensation. If you don't believe my words, just go to the previous year question papers, flip the pages, and you will see almost every year you are getting a question from this particular area. So I will try my level best to give you the conceptual clarity as far as this particular topic is concerned. But you have to be in the session till the last moment. Then only you will be able to get some benefit out of it. Before we proceed, everybody just quickly like the session, share it with your friends and colleagues, and do not forget to subscribe to BYJU'S Exam Prep YouTube channel. If you have not subscribed till now, do not forget to subscribe it. Hit the bell icon so that you get all the important notifications in time. So everybody who is joining me live, just quickly confirm your presence in the comment section. You have to be more proactive in the comment section so that I am also motivated, so that I can motivate you also. Good evening, Tharani. How are you? Welcome to the session. So let us quickly start with the session. Some of you may be joining me for the first time. So there is a brief introduction about me. My name is Ashutosh. As you can see on the screen, I have 11 plus years of teaching experience, completed MTech from ITBHU in 2010, written a couple of books on engineering ethics and power system. And my areas of expertise are power system, electrical machines, electromagnetic field theory, material science, and obviously engineering ethics. Before we proceed, I want to make a very proud statement about the exemplary result we have got for GATE 2022 examination. If you see, we have got 41 selections under rank 50, 11 selections under rank 10, and 74 selections under rank 100. So our aspirants shine again. Some of the top rankers like Ram Balaji from electronics, rank 1, Vandit Patel, rank 2 from electrical, and rank 3 mechanical, Parvinder Singh Dhonkal. So you can be in this frame next year if you prepare and you attend some of the important session that we are trying to give you. Now let us try to understand what is the agenda, what are the topics we are going to cover in this particular session. First, we are going to talk about what is the nature of power system components. If you want to solve a problem, the first thing you have to understand the problem. So in this part, we are going to understand the problem. Why we are talking about the reactive power compensation, that we will discuss. The second part is, we will talk about the types of compensation, various types of compensation, whether it is static compensation, whether it is dynamic compensation, or whether it is solid state devices compensation. That is what we are going to discuss in the second part. In the third part, I am going to give you a brief idea about the various types of compensation. You must be knowing this, that it is not possible to complete everything in a 45-minute session, but I will try my level best to give you enough confidence in this particular topic. And once the session is over, if you have any confusion, any doubt, any query, you can join my personal Telegram channel that is available on BYJU'S Exam Prep, that is Electrical by Ashutosh Saxena. You can raise your queries in this particular Telegram channel. Is it clear, everybody? Just tell me in the comment section. Is it clear, everybody? Shall we proceed? Yes, Tharani. So let us first talk about the nature of power system components. The first thing you have to answer me, what are the different types of components that you can have in your power system? The first most obvious answer is going to be synchronous generator. That is the most important part of our system because it gives us electrical power or energy. So let me first talk about the synchronous generator. Now when we talk about the synchronous machine or the synchronous generator, you know that there are three types of operation. The first is overexcited condition. In the overexcited condition, the basic idea is that your machine is going to behave as a source of lagging reactive power. Source of lagging reactive power. It is important to use this adjective lagging. Are you getting this? If you have studied synchronous machines properly in your subject machines, then it will be very easy for you to understand. But even if you have not studied well, I will give you practical understanding that how you can identify what is going to be the load condition when we are having overexcited, underexcited or level excited condition. So the first thing we are saying about the overexcited condition is that your generator is going to be acting as a source of lagging reactive power. The second thing is, for overexcited condition, mod EF cos del is going to be more than mod V, where EF is the excitation EMF, del is the you can say load angle or torque angle you can say, and V is the magnitude of the terminal voltage. This is the condition for overexcited condition. Now please try to understand what is the basic nature of generator. The basic nature of generator is to supply power. Yes or no? If I am a generator, then what is my basic nature? My basic nature is to supply power, whether it is real or reactive. In the overexcited condition, you are saying it acts as a source of lagging reactive power. So if I ask you what is the operating power factor, whether it is lagging or leading, so what is your answer? Your normal behavior is supplying the power. What you are doing? You are supplying the lagging reactive power. So what is the operating power factor? It is going to be lagging power factor. Is it clear? Everybody just tell me in the comment section, are you able to follow this? How you identify? You don't need to draw the difficult phasor diagram because in machines you can do that. In power system, you may not be having that much of luxury of time. So you can use this concept. What is the basic nature of generator? To supply power. What it is doing? It is supplying the lagging reactive power. So what is the operating power factor nature? It is lagging in nature. Are you able to follow me? Everybody just tell me in the comment section. Second condition is underexcited condition. Underexcited condition, what is happening? Your generator is going to act as a sink of lagging reactive power. What is the meaning of sink of lagging reactive power? It means in the underexcited condition, your generator is going to absorb, act as a load for the reactive power, lagging reactive power. What is the condition? Mod EF cos del is less than mod V. And what is the operating power factor? Now you can judge. Now you can guess it. What is the basic nature? What is the basic nature in the underexcited condition? The generator is, whether it is underexcited, overexcited or any type of excitation is there, the basic nature of the generator is to supply power. But you are saying no, it is acting as a load, it is absorbing the lagging reactive power. So if I say, suppose one of the students in my class, after the class he is coming to me and he is saying, sir, I don't have money, I need 100 rupees to buy a chocolate. So I will give him 100 rupees. But he is not a good guy, he is a bad guy. Now he will go to his friends and he will say, you know, Today I have given Ashutosh Sir minus 100 rupees. Actually what he is saying is right. Technically that is right. I give him 100 rupees means he has given me minus 100 rupees. The same logic you can apply here. If you are saying your generator is acting as a sink of lagging reactive power, it means you can say it is acting as a source of leading reactive power. I hope you are getting my point. So if your basic nature is supplying the power, so you have to understand accordingly. Acting as a sink of lagging reactive power means actually you are supplying the leading reactive power. So what is the operating power factor? Leading. Everybody just tell me in the comment section. No need to draw the difficult phasor diagrams. Just by using this practical common sense, you can identify under excited condition it is leading, over excited condition it is lagging. Is it clear? Everybody just tell me in the comment section. Yes, Sarani. It is not lagging, beta. It is leading. Because the basic nature of generator is to supply the power. Here you are saying it is a sink of lagging reactive power. Sink of lagging reactive power means source of leading reactive power. So what is the operating power factor? Leading. See the third condition. The third condition is level or normal excited. Level or normal excited condition means what? Neither as a source nor as a sink of lagging reactive power. Yes or no? So what is the condition? The condition is mod EF cos del is equal to mod V. And the power factor nature is going to be what? Unity power factor. Directly you can understand. Is it clear, everybody? So we have talked about the nature of synchronous generator. Now let us talk about the synchronous motor. Now let us talk about the synchronous motor. Again there are three conditions. Number one, overexcited condition. Overexcited condition. Again it is going to act as a source of lagging reactive power. What is the condition? The condition is mod EF cos del is more than mod V. Now please try to understand when you are saying synchronous motor. So what is the basic nature of motor? The basic nature of motor is to absorb power. What he is doing here? Source of lagging reactive power. It means, in other words, you can say it is a sink of leading reactive power. So what is the operating power factor condition? Operating power factor condition is going to be leading, just the reverse of synchronous generator. Similarly, you can talk about the underexcited condition. Now I hope you understand well. For the underexcited condition, your motor, synchronous motor, is going to act as a sink of lagging reactive power. What is the condition? The condition is mod EF cos del is less than mod V. And what is the operating power factor? It is a motor. What is the basic nature? The basic nature is to supply power. What he is doing? Sorry, what is the basic nature of motor? To absorb power. Absorb power, yes or no? Consume power. So it is acting as a sink of lagging reactive power. So what is the operating power factor? It is lagging. Yes, perfect, Tharani. Now you understood the concept. Third condition, level or the normal excited condition. Level or the normal excited condition. it is going to be acting neither as a source nor as a sink of lagging reactive power. Is it clear, everybody? Just tell me in the comment section. Yes, everyone? So what is going to be the condition? The condition is going to be mod EF cos del is equal to mod V. And what is the nature of operating power factor? This is going to be unity power factor. So we have talked about the synchronous machine, we have talked about the synchronous generator, we have talked about the synchronous motor. Now what is the next power system component we can discuss? Everybody just tell me in the comment section. Can you guess it? What is the next power system component we can discuss? The next power system component is going to be, suppose, induction generator. Now you must be knowing that induction generator we are also calling as asynchronous generator. Why asynchronous generator? Because it does not operate at the synchronous speed, whereas the synchronous generator operates at the synchronous speed. That is why we are calling it asynchronous generator. But there are some problems with the induction generator. What are the problems? Induction generator operates on the principle of induction. The principle of induction is the same principle that you are using in the transformer. Yes or no? What is induction principle? Induction principle means you give excitation to one winding or the one system, and the other system currents are going to be induced. Now because of this nature, this induction principle, your induction generator cannot generate reactive power, and your induction generator can only generate real power. And for the reactive power, it is dependent on some external source. It may be your grid, it may be some local reactive power management or compensation. So the first thing you understand that it is always going to act as a sink of lagging reactive power. Everybody just tell me in the comment section, are you able to follow this or not? Now let us talk about the induction motor. Induction motor is always going to be a sink of lagging reactive power. What is the next component we can discuss? We can talk about the transformers. As I told you, transformers also work on the principle of induction. When the principle of induction is there, definitely reactive power is required. Whenever induction principle is there, it is going to act as a load in terms of the lagging reactive power. So its basic nature is, it is going to act as a sink of lagging reactive power. Then let us talk about transmission line. Now your transmission line also have three conditions. Number one, when the loading is more than surge impedance loading. I hope you know what is surge impedance loading. If you don't know, I will tell you, or in some other session I will tell you. Yes, both induction generator and induction motor, they are dependent. They act as a load for the lagging reactive power. That is why they are going to act as a sink of lagging reactive power. When the loading is more than surge impedance loading, what is happening? You are saying, what is the reactive power absorbed? The reactive power absorbed is I square XL. What is the reactive power generated in the transmission line? That is V square upon XC. In this condition, the reactive power absorbed is more than the reactive power generated. What it is going to happen? What is going to happen? Your transmission line is going to behave as a sink of lagging reactive power. Is it clear, everybody? Just tell me in the comment section. The second condition is when the loading is less than surge impedance loading, the reactive power absorbed is less than the reactive power generated. This is the reactive power generated and this is the reactive power absorbed. So what is going to happen? It is going to act as a source of lagging reactive power. And if you want to know, I can tell you that this is the condition because of which you get the Ferranti effect. And this is the reason why you are getting the no load or the light load condition receiving end voltage more than the sending end voltage, because actually your line is acting as a source of lagging reactive power. And let me tell you a very simple classical concept. What is the classical concept? Suppose this is a node in your system. You understand what is a node in your system? Where two or more than two network branches are going to be connected. That is what we are calling as a node. Now suppose the reactive power generated is this and the reactive power absorbed is this. Are you getting this? And suppose this is the voltage. So we have three conditions. Number one, if the reactive power generated at this node is more than the reactive power absorbed, the basic concept is that the magnitude of the voltage of this node is going to be increased. If the reactive power generated is less than reactive power absorbed, then the magnitude of the voltage of this node is going to be reduced. And if the reactive power generated is equal to the reactive power absorbed, then the magnitude of the voltage is not affected. Everybody just tell me in the comment section, are you able to follow this? Is it clear, everybody? Only one or two candidates are responding, rest are just watching it like a movie. But that is not good. You have to interact as much as you can. Is it clear? So by using this logic, you can understand for the three conditions how your transmission line is going to behave. The third part is when your loading is equal to surge impedance loading. In this condition, the reactive power absorbed is equal to the reactive power generated. This is reactive power absorbed and this is reactive power generated. So we say that your line acts neither as a source nor as a sink of lagging reactive power. Yes, Manish, Niranjan, all of you. So we talked about transmission line also, transformer also. Let me just talk about a static or let me write it better. It is pure inductive load. Pure inductive load means what? Please try to understand. Suppose this is your line and suppose this load is pure inductive load, something like this. Yes or no? Is it clear? Now this bus, suppose the voltage is V angle 0 degree. We have assumed it V angle 0 degree. Now the current taken by this pure inductive load is going to be what? It is going to be a lagging current. Lagging current means the current is lagging in terms of the phase angle with respect to the voltage phase angle. So if this is the reference V angle 0, so this is going to be IL angle minus phi L. Can I write like this? Very simple. Even a KG fail student can do this, and I hope there is no KG fail student in my class. Can you draw the phasor diagram? If this is your voltage, this is going to be your current. Yes or no? So what is statement, what conclusion I can give? I can say that the pure inductive load is going to act as a sink of lagging reactive power. Yes or no? But GATE is not an easy exam. ये गेट नहीं आसान, बस इतना समझ लीजिए, एक आंख का दरिया है और डूब के जाना है, तैर के नहीं जाना है। एक आंख का दरिया है, तैर के नहीं जाना है, डूब के जाना है। GATE is not going to ask you this simple analysis. GATE is going to ask you this. Okay, so we are running short of pages. No problem. We will discuss this later on. In other words, what you can do, suppose this is the line, this is your inductor, the voltage is magnitude V angle 0 degree. Listen very carefully. I am going to reverse the direction of current. I am going to reverse the direction of current. In the previous diagram, this pure inductive load was taking the current from the system. So we were saying it is acting as a sink of lagging reactive power. But now I have reversed the current direction. If I reverse the current direction, how I am going to write the current? IL angle minus phi L, but I have to put a negative sign because I have changed the current direction. Are Baba, yes or no? I have changed the current direction. So how I am going to draw the phasor diagram right now? The phasor diagram is going to be like this, V. Now actually you are making the pure inductive lagging current like this, but you want minus of this. So minus of this is going to be like this. Yes or no? So this is going to be your minus IL. Angle you can understand. Now this current is not taken by the inductive load, it is supplied by the inductive load. So what is the statement conclusion you can draw? You can say in this particular construction, in this diagram, you can say your static inductive load is going to act as a source of leading reactive power. Everybody just tell me yes or no in the comment section. Why source? Because it is supplying the current, supplying the power. Why leading? Because the current is leading. I hope you are getting this. So whether you say sink of lagging reactive power or source of leading reactive power, the idea is same. But generally we are not talking in terms of the leading. We are talking in terms of the lagging reactive power. So most of the cases we are assuming that your inductor is going to absorb the reactive power. We are not mentioning whether lagging or leading, but if you are a good engineer, you will always mention whether you are writing it for the inductor or the capacitor. When you say it is going to act as a sink, you must say it is going to act as a sink of lagging reactive power. When you say like this, you will say it is going to act as a source of leading reactive power. Similarly, you can talk about the capacitor also. Suppose you are going to talk about the capacitor. Pure capacitive load. Now the pure capacitive load, this is going to be your line, and suppose this is your pure capacitive load. Again the voltage is V angle 0 degree. Suppose the current taken by this load is IC angle plus, sorry, one small mistake I have done. Please correct it. It is not going to be phi L, it is going to be 90. Why? Because it is a pure inductive load. It is going to be a pure inductive load. So this is directly 90 degree. Here also you can change, it is directly 90 degree. I hope you understand. Is it clear? Because it is a pure one. Good evening, Shubda. Good evening, Suman. How are you? Welcome to the session. So similarly, you can talk about the capacitor, and capacitor is going to have a leading current. How much leading? 90 degree leading. How you are going to make the phasor diagram? This is going to be your voltage, and the current is going to be leading by 90 degree like this. So what is the conclusion you can make? A capacitor is taking, capacitive load is taking current. What kind of current? Leading current. So you can say it is going to act as a sink of leading reactive power. Leading reactive power. Similarly, again you can change the current direction and you can get the other statement. You can say this is your line, this is your capacitor, this is the voltage angle 0, and if you change the current direction, instead of taking the current, suppose this capacitor is supplying the current, so you have to write one minus sign and this is going to be plus 90 degree. How you are going to make the phasor diagram? This is the voltage. Now generally for the leading current you are drawing like this, but because a minus sign is placed before this, so you have to take the opposite of this, that is like this, minus IC. So what is the conclusion statement you can give here? You can say the capacitive load, pure capacitive load, is going to supply what? Lagging reactive power, or it is going to act as a source of lagging reactive power. At least say yes or no in the comment section. Yes. You can also appreciate if you are getting the concept. You can send me some good emojis to show your appreciation. If not, then also you can send. Okay. Anyways, so this is what we have discussed, the nature of various power system components. Now I am going to talk about the types of compensation. Types of compensation. Generally we have three types of reactive power compensation. The first one is static compensation. Then we have dynamic compensation. And then we have solid state devices compensation, or simply solid state compensation. Let us first talk about the static compensation. Why we are saying it is a static compensation? So thank you so much for your emojis, Shreyansh. I feel little better in this very hot summers. Thank you, Tharani. What do we mean by static compensation? Now please try to understand. I will give you a very practical live example for that. Suppose you are waiting for some guest to come in your home. So what is the best thing you can do in order to save time? Before the guests are going to come, you can prepare some snacks. Yes or no? And whatever is the demand of the guest, because you have already prepared the snacks, so how much rasgulle they want, you can offer to them. You want one rasgulla, take it. Already it is available. 2 rasgulla, take it. 5 rasgulla, take it. 10 rasgulla, okay, tata, bye bye. You can say like that. Yes or no? Yes? The same thing is happening with the static compensation. Suppose this is your bus where you want to provide the reactive power compensation. And suppose you are using a shunt capacitor bank. Number of shunt capacitors we are using. Something like this. These are the switches. These are the switches. This is your line which needs compensation, and these are your shunt capacitors connected like this. Whenever you want to provide some reactive power compensation, you want to add that capacitor, you just close the switch. Suppose this is going to be, every capacitor is going to have a rating of 5 MVAR. So any switch you are connecting, you are providing 5 MVAR additional reactive power compensation to the line. Suppose if you are closing one switch, what is the compensation you are providing? 5 MVAR. If you are closing two switches together, you are providing 10 MVAR. If you are closing 3 switches, 15 MVAR. 4 switches, 20 MVAR. All the 5 switches closed, 25 MVAR. Now one thing you will understand, if the situation is like this and I ask you, can you provide me 12.5 MVAR compensation, you will say not possible. It is only possible in the multiple of basic fundamental unit of compensation. Basic fundamental unit of compensation here is 5 MVAR. So you can only provide compensation in the multiples of this basic compensation, that is 5 MVAR. So that is why we are saying that the static compensation is not smooth. It is not smooth because any compensation value is not available. Only multiples of basic unit is available. So the first property of a static compensation we are getting is that it is not smooth. It is not smooth. But there is one advantage also. What is the advantage? The moment guest is coming, he is asking 1 rasgulla, you are saying take it. It means the compensation is going to be very fast. The compensation is very fast compensation. The moment you require the reactive power, just close the switch, you will get it. There is no time lag. Everybody just say yes or no in the comment section. Yes, everyone. Let us talk about the dynamic compensation. Dynamic compensation, we are using synchronous motor. And we are calling it dynamic. Why dynamic? Because it is real-time compensation. Why it is real-time compensation? Because the compensation is not available in the multiples of basic unit. Whatever is the requirement, if that can be supplied by the synchronous motor, it is going to be supplied. Whether you ask for 12.5 or you ask for 12.555, whatever is your requirement, that can be supplied. So any value of compensation is available. That is why we are saying it is a smooth compensation. So dynamic compensation is going to be a smooth compensation. But at the same time, there is one disadvantage also. Because we are using synchronous motor has a mechanical system, rotating system. Whenever mechanical system is involved, it is going to be some time delay is there, because mechanical time constant is very high comparatively. So it will take some time to process that compensation. So we are saying it is not that fast compensation like your static compensation. So it is not that fast. It is not that fast. Not that fast. Now, if you have two friends, one friend is having one disadvantage, one advantage, and one friend is having one advantage, one disadvantage, then what should be your objective? Your objective should be that you take only the advantages of both of your friends. And that is what solid state devices compensation is doing. They are using power electronic devices to have the dynamic compensation. When you are using solid state devices, there is no rotating part, no mechanical time constant is involved, so they are going to be very fast. And because you are using power electronic devices, you can control the firing angle, you can have any degree of compensation. So it is smooth also. It is smooth also. Everybody just tell me in the comment section, are you getting this or not? Yes or no in the comment section. The complete idea of types of compensation I am getting out of the frame. If you want, you can take a snapshot. It is going to give you one question in the gate. Is it clear, everybody? Yes or no? Perfect, Tharani. So this is about the types of compensation. So let us have some brief idea about the various compensation. The first compensation that I am going to discuss is shunt capacitor compensation. Suppose this is your generator, this is your transmission line, and this is your load. Okay, suppose the real and the reactive power sent from the sending end is like this, PS plus JQS, and this is mod Vs. Suppose this is angle del, this is mod VR, take it as a reference, angle 0, and here you are placing a shunt capacitor. So what this shunt capacitor is going to do? This shunt capacitor is going to provide some lagging reactive power to the system. Just now we have discussed. This shunt capacitor is going to supply lagging reactive power to the system. Is it clear, everybody? Just tell me in the comment section. So I am going to tell you some basic formulas that are going to help you in solving the problems. The first thing is, by applying this shunt capacitor, what is going to happen? There is going to be a voltage rise. What is the expression for that voltage rise? It is going to be X Q shunt capacitor divided by mod Vs. This is Q shunt capacitor. What is Q shunt capacitor? It is the lagging reactive power supplied by the capacitor. So delta Vc is the voltage rise. Where is the voltage rise? At the receiving end. At the receiving end. This voltage rise delta Vc we are defining as mod VR2 minus mod VR1. What is mod VR2 and what is mod VR1? Mod VR1 is receiving end voltage without shunt capacitor, and VR2 is receiving end voltage with shunt capacitor. I hope it is clear. You can directly use this formula. After the voltage rise, there is going to be some improvement in the power factor. And let me tell you, even if you are getting some voltage rise by applying the shunt capacitor, but your shunt capacitor is generally not used for improving the voltage profile. No, not. Shunt capacitor is used to improve the power factor of the system, not the load, because once you design the load, the power factor of the load is fixed. You can't change it. You can just improve the system's power factor. How you are improving the power factor of the system? Suppose without shunt capacitor, what is the case without shunt capacitor? Suppose this is your voltage, receiving end voltage, yes or no? And because generally this load is going to be a lagging load, we are assuming this is a lagging load. So the current drawn at the receiving end is going to be something like this. The current drawn by the load. So this is going to be I angle minus phi 1. Why minus? Because it is lagging phi 1. So this angle is going to be phi 1. Now what is happening with shunt capacitor? See what this capacitor is doing. This capacitor is actually drawing a leading current plus 90 degree from this receiving end. Additional current it is taking, that current is leading. So now if you have to draw the phasor diagram, it is going to be something like this. This is your voltage. This is your current taken by the load at the receiving end. And this is your leading current taken by the shunt capacitor. But when you are adding the shunt capacitor, what is the total current in the line? Suppose this is IS2, previous one is IS1 without shunt capacitor. So this IS2 is going to be the addition of this current and the current taken by the capacitor. So in the phasor diagram you have to add this current. If you add this current like this, what is the final one? The final current IS2 is going to be something like this, and it is going to lag by some angle phi 2. This total angle was phi 1. Now you see very easily from the diagram you can say phi 2 is less than phi 1. So cos phi 2 is going to be more than cos phi 1. So can I say power factor for the second case is going to be more than power factor for the first case? So 100% you can say there is a power factor improvement. Is it clear everybody? Just tell me in the comment section. Hello Anurag, how are you? Welcome to the session. So we are beyond the scheduled time. Okay, beyond the scheduled time. So everybody in the session, just tell me, you want me to continue for 5 more minutes or we should stop? It's your choice. Yes, DC Kumar Sena. If you are interested, we can continue for 5 more minutes. And if you are not interested, we can leave. We can leave. So what is happening here? Listen very carefully. If you tell me the reactive power supplied by the shunt capacitor, this you can write. See, whether you say stop or whether you say continue, you are not going to decide, because I can decide, you can't decide. Only I can decide, na? So listen. So the reactive power supplied by the shunt capacitor you can write as P load, and that is tan phi 1 minus tan phi 2. You know what is phi 1, you know what is phi 2, you know what is P load. This is P load. This is P load. Is it clear everybody? One more equation you can write for the reactive power supplied by the shunt capacitor. If it is a 3-phase, you can write 3 times V phase square upon XC per phase. Now what is XC per phase? XC per phase is the shunt capacitor you are providing per phase. So that XC per phase you can write as 1 upon 2 pi F capacitance per phase. So if you put it here, it is going to be Q shunt capacitor is equal to 3 times V phase square, and this is going to be 2 pi F capacitance per phase. So one more important equation that you can follow. Is it clear, everybody? Just tell me in the comment section, are you able to follow this? So friends, let me stop here because we are much beyond the scheduled time. Tomorrow we have a session in which we have to discuss the questions related to what we have read today. So there are some more types of compensation which I want to give some concept, on which I want to give some concept to you. So before we start questions in the tomorrow's class, I will give you that theoretical backup, that understanding I will give you, and we'll discuss some important questions. So this was all from my side for today's session. Thank you so much for joining me live in the discussion. It was a great time talking to all you guys, and do not forget to join me again tomorrow 8 p.m. in the evening. I will be live and I will be discussing problems on reactive power compensation apart from other important types of compensation that we have left today. Thank you so much, everybody. If you have any query, any doubt, you can join my personal Telegram channel on BYJU'S Exam Prep, that is Electrical by Ashutosh Saxena. Once again, thank you so much. Stay connected. All the best. Thank you. Thank you, everybody. Thank you, everyone. Take care.